Right. Hi, everyone. Good morning. Welcome back. We have a fantastic session lined up for you today, one that sits right at the intersection of AI and quantum computing. And we have a wonderful speaker with us today. We have Dr. Taylor Patti, who's a research manager in the Quantum Simulations and AI Research Group at NVIDIA, where her work spans everything at the intersection of quantum, classical, and quantum and AI. She is looking into quantum algorithms and machine learning for different applications, right from the efficient simulation of quantum systems to doing optimization and so on. She holds a PhD in theoretical physics from Harvard University, where she was advised by Professor Hussein Ellen. Today, Dr. Patti will be giving us a sweeping look at how AI is advancing quantum computing. Please join me in welcoming Dr. Taylor Patti. Over to you, Taylor.
Well, thank you so much for the wonderful introduction. Let me just pull these slides up. We already tested, so I know you can see these slides, but just for redundancy's sake, can you guys see these slides?
Yeah.
Okay. Well, that's just in that case, I'll jump right in. Thank you so much, Abinaya, for the wonderful introduction. As she said, my name is Taylor Patti, and I'm the manager of the Quantum Simulation and AI, or QSI Research Group at NVIDIA. We're part of NVIDIA Research, which is the most kind of like, I don't want to say unapplied, but we're the most maybe pure research part of the NVIDIA organization. We're only about 400 people in a company of about 40 something thousand. So we're small, but hopefully mighty. And yeah, and my talk is all about how to use HPC, like high performance computing and GPUs, and AI, artificial intelligence, to help build better quantum devices, control them better, study quantum physics, all these good things. So before I get into what my talk is going to be about, I want to talk about what my talk won't quite be. So what my talk won't quite be is it won't be like a broad and democratic overview of all the different things that everybody is doing in AI for quantum. And I'm not doing that because I feel like there's already a lot of good resources. There's a lot of good review articles, such as this review article from me and my colleagues of last year. But there's a lot of other good review articles too, a lot of good YouTube channels, like whatever. There's a lot of good resources. So I want to do something that's still panoramic. I still want to show you guys a lot of different examples of good research being done in the quantum sciences. But I'm going to do it somewhat narrower and much less democratic. I'm basically going to show you mine and my group's work with our many, many wonderful collaborators. And our collaborators are so numerous and so diverse in their expertise and their applications that it's actually going to be pretty broad. Okay, it's not going to be much narrower than a review article because we have some great collaborators who do all sorts of things. But it's going to be much less democratic because it's going to be all research that by definition, like a priori, right, I think is good. I think this is the way you should do HPC, high performance computing. By that, by the way, guys, because I know there's all levels of folks here. I mean, big computers, GPU clusters, things like that, and AI for quantum devices. And so the two things that I think should be incorporated to research, that makes us not democratic, that I think should always be present, are the following two things. Hopefully you see it in all the different research projects we're going to speed date here in a minute, are that I think is important to, before you train a model, remember to have a well-balanced computational diet. And what I mean by that, hopefully you guys can see my cursor. A lot of people, they jump right to these steps. This, by the way, for those of you who were raised in the United States in the 90s and 2000s, this is how they taught us to eat. This is how they said we should organize our food. Here's the food pyramid. Bread was the most important meal for some reason. I think they've reformed this guidance. But anyway, I think that the bottom of your food pyramid, right, if you will take my 1990s and early 2000s analogy, should be all about efficiently simulating your quantum system. And why I say this is because ML and actually building and controlling quantum devices, quantum computers, always rests upon data. And in today's landscape, quantum computers are very rarely giving us enough high quality data, and enough of it, right? The millions and billions of data points that we need to train really great ML models a lot of the time. Usually there's a huge dearth, a huge lack of the data that we need. And so I think it's worth taking the time to fix this. So basically almost every project we'll talk about today fills out the bottom of this pyramid and gets you the simulation data that you need to go ahead and train the AI model, because we don't usually have it from a quantum device, at least not in the scale that we need. The other thing I think you guys should always do, and hopefully you see reflected through almost every project that we're about to see, is the importance of being as lazy as possible. So what I mean by this is you need to not give your AI model something that's too hard to learn. You be ambitious in your applications, but lazy in your implementation. So this is because the way that ML works, right, is we say, ML, here's a problem for you. And we define our problem basically for a loss function, right? Here's a pattern I want you to find. And I'm telling you which pattern I want you to find through the loss function that I have for you. I'm going to give you data, and you're going to figure out this pattern, right? Well, if I give it a hard pattern to learn, it's going to need a lot of data. And it might need to be a bigger model with more parameters. It might also need to have more training steps. It's going to be computationally hard. And this is easy to give too hard of a pattern in quantum systems, right? Quantum systems are in general exponentially complex. If you tell your ML model to figure out an exponentially complex pattern, if you tell it to find the full wave function, in many cases, unless you have a very fixed finite scale that's useful for you, this is going to, you're going to have a bad time, right? It's going to take too much data to learn. So instead, look for something more compact. For instance, an expectation value when you can. So that there is infinite value in being a little bit clever to be as lazy as possible. So these are the two things that I think that you'll find reflected throughout most of these projects. And I hope that you actually apply them as well into your own research, because I think these are the two of the most important things to keep in mind for modern research into HPC and AI for building quantum computers and better in quantum devices. Okay, so with that, let's jump in to like a myriad now of different research projects that me and my group and our wonderful collaborators have done. And again, this is going to be kind of like a speed dating type feel. So we're only going to spend between 1 and 3 slides on any given set of projects. Then we're going to move on to the next one. And I want to give you guys like a review article of my group's research, right? And the research we do with other folks. So the first kind of subset of topics I want to talk about is all revolving around ML decoding for quantum error correction. And so quantum error correction, for folks who are not familiar, is this kind of essential idea. You know, we all know that very easily argued the most pressing issue facing our quantum computers is noise, right? That's a really tough nut to crack. So one of the ideas that people think that we need to protect them from noise is quantum error correction, which is basically taking groups of qubits, what we call physical qubits. These are the qubits that we all know and love, organizing them to hold the data of just one qubit. And then because they're a group of them, we could actually do clever measurements. We call these syndrome measurements on them. We could read out the syndromes, and we call them stabilized measurements. We could read out the syndromes, and these syndromes tell us two things. Did an error occur? This is easy. If the parity is, 1 instead of 0, an error occurred. And also, how do I fix this error? How do I fix this error is tougher. And here's where the AI model comes in, because it's not apparent to a human for most cases and most codes, especially at scale, that, when I get this sequence of 0 and 1s that are these measurements that are my error correcting measurements, right, is not clear to me, at least, and to anybody that we know, how exactly, especially really quickly as you correct your quantum device, how exactly you need this corresponds to you needing to fix your qubit register. And so the idea is to have an AI decoder that we train with lots of noisy data that then tells us, oh, you bit flip this one and phase flip this one. And if it does a good job, you get a perfect register of qubits. You can do your quantum computation. You could factor RSA, and steal everybody's credit card. And if you do a bad job, well, you probably just make the situation worse. So now folks have been working on these AI decoders. They're a very hot topic right now, but there's kind of a fundamental trade-off in this data collection issue, right? This bread and fruits and vegetable part of the pyramid. And that is, how do we get enough high quality training data to do this? Actual quantum devices, they're too slow to get data from. First, get the huge data corpuses of millions and billions of data points that we want here. Traditional simulations, like the state vectors and stuff, those are good, but they're quite slow. It's really compute intensive. And a lot of people use something called Clifford gates. And so these are a subset of quantum gates that if you only do them, simulating your quantum system grows only polynomially. So then again, you get millions and billions of data points. However, as you might imagine, if you're only doing certain gates, then you're not really faithfully representing your quantum system. You're really looking at like a shadow of it, basically, but not the whole thing. And so we wanted to improve this middle ground. We wanted to improve this simulation with something that we call pre-trajectory sampling with batch execution. The idea is I'm going to do high quality state vector simulations, and I'm going to do them in a way that no one has done them before, so that I get a lot of data really quickly. I want the best of both worlds. I don't want low quality data or partial data. I don't want a little bit of data. I want a lot of good data. And so it had other benefits as well, but the best part is that you get big old data. So here's kind of the gist of the situation. The way that other people would do it is they would, define their noisy quantum system. They would then one at a time randomly sample the errors that they were going to do. Then they would build a state vector. This is a stochastic state vector, so it's like stochastically sampling the errors, and then building a state vector with that and sampling it once, rather than the density matrix formalism, which some of you might be familiar with, which scales exponentially worse. So we didn't want that. But what we did was something actually quite simple, right? We defined our noisy quantum system as people had before, but then we just upfront calculated all the different errors that we would do and decided based on their characteristics how many shots or measurements we would take of each. Then we would build each state with the corresponding errors, and there's no getting around building each state, and that is exponential work. But then we would sample as many measurements or shots as we wanted from just a single state preparation, which is much better than doing it one at a time, because the sampling itself is only polynomial complexity as well. So here we got basically more shots for free. So if you want to have your shots sampled perfectly, such that it's completely correspondent with your quantum statistics, then you're going to get like 100 to 1,000 times speed up depending on the system. But if you just want a lot of data because you want to train one of these AI decoders and you just want a lot of data to do that, then you could easily get millions of times speed up of your data collection. So like for instance here, if you take 1 million shots each, you just want a lot of data. These are really complex systems. A lot of data will do you good. You get like 1 million times speed up. And so this is just like a kind of a clever refactorization of how you do these things. We also extended this to something called tensor networks. So tensor networks will come up a couple times in this talk. For those of you who are not familiar, tensor networks are, they're like a generalization of state vectors, right? So you guys are probably familiar with state vectors that as soon as you build them, right, you have like n qubits and they scale to the n because we're already allocating all that memory right up front that this is, at max, how complex my state will get. Well, with tensor networks, you don't do that. Your state grows in complexity and therefore the amount of memory it takes up on your GPU and therefore the amount of compute that you have to do to operate on it. It grows in memory as you add gates or time evolution or however it is that you're representing the entanglement and the growth of your quantum system. And so this is a really good way to do this as well, because if you have shallow circuits with tensor networks, you can simulate hundreds or even thousands of qubits, which of course you could never do with a state vector, not if you took the whole universe up, right? So, and classical hardware. So we improved the tensor network version as well, with just like a lot of clever, simple tricks. Without getting too much into the weeds, with tensor networks, you need to decide how you're going to do your operations in what order, called a contraction path. Well, we devised a way where you could use the same contraction path for all errors, which before people calculated that each time, it's very expensive. We also kind of refactored the work so that you never repeated redundant work. You kind of cached that intermediate and used it later. And we also got really fine-grained with how the contractions were done. We found a more efficient route, which sped it up a lot. And this resulted in general, kind of adhering to quantum statistics, sampling being 100 to 1,000 times faster, as you see here, for different configurations depending on your quantum system. And this kind of big data, I just want more data, I want to train an AI decoder, data collection being about 10 to 100 million times faster. So it's a lot more data. And if you have 100 million times more data, let me tell you, you could train your system much more easily. You could train your AI model much more easily and do a much better job. Okay, so with that, I'm going to move on to another series of talks of projects. And this is going to be a little bit of a different vibe, but it's going to still fit this theme of human ingenuity, right, for doing better data collection for then training a model. So this one's going to start maybe in inverse order. I'm going to start with the model that we trained first that taught us that we needed better data collection. So this is a project that is all about using ML models for what we call charge stability diagram interpretation. A charge stability diagram are these diagrams right here. I'll get into them in a second. And these are really important for studying semiconducting qubits, which we also call quantum dots. So these are qubits that are built on semiconducting materials, which is the same material that we build regular computers on, but they of course manipulate them in a very different way. So you'll be seeing in a lot of these research projects, you'll be seeing a student here in the corner. This student who led the work, his name is Rahul Marchand, and he is about to graduate, I think, quite soon here from Oxford, University of Oxford in the UK. And he was a lead on this project, and I'm going to show you guys these students every time. Number one, because they're the ones who do the hard work, right? They're what Teddy Roosevelt would call the person in the arena. But number two, because I know that many of you are students, and I think it's useful to remember that actually a lot of us physicists do our best work in our 20s. As someone who's not in their 20s anymore, this is sad for me, but really you do a lot of your best work in grad school and undergrad. You even see that reflected in who won the Nobel Prize. A lot of times they won the Nobel Prize. They might have gotten it when they were 60, but it's for work that they kicked off when they were in their 20s. So just remember, as you go through school, that like what you're doing right now is actually quite relevant to your life and career in science. And a lot of times, like a lot of the biggest research going on, it's driven by people who are your age. We're a little bit older or something, but just about your age. But anyway, okay, so get used to seeing the students in the corner here. So back to the research project at hand, this was an AI project that taught us that we needed better data collection. So the semiconducting qubits, basically you take a semiconducting material, which is again this kind of thing that you have sitting in your computer watching this right now, and you carve or you deposit different features. So these little features, they call them gates, which is confusing for the rest of the quantum computing world. We think of gates as logical operations, right? But basically, with each of these little features that they deposit or carve, they apply some voltage. And when you look at a cross-section of any two of these voltages, and this is a big dimensional space because each of these features has its own voltage. When you look at the cross-section here, you could draw these nice charge stability diagrams, which basically tell you as a function of energy or a function of voltage, how your charge carriers are sitting, which tells you how to operate this device. So we wanted to train, because it's so large, has such a big dimension, we wanted to train an AI model to interpret these for us. So we chose a transformer model back with a convolutional network. So this guy is really good at looking at pictures, and this is represented as a picture. And Rahul very successfully trained this thing to recognize the boundaries between these basically these density. This is where there's high density or low density of electrons. You train it to really efficiently locate the boundaries and these triple points, which is where two boundaries meet. So this is really needed in that field. So Rahul did a great job. We got a great result, but this project left us a little bit displeased with our data collection because there was a nice package called QArray that you could use for this data collection, and it's a really quality open source package, but we wanted it to be faster. And so Pranav, who is just about to graduate, also from the University of Oxford in the RS group, he took over working on this, and we wanted to make QArray faster so that we could get more data and better quality data. So QArray does these same charge stability diagrams. Like, don't be fooled just because it's a different color. This is the same concept, right? So QArray did these charge stability diagrams, and the typical way that these are done is a semi-classical approximation. So not everything is represented as quantum, basically. So we wanted to make it better and faster. So the first thing we did is we wanted to add stochastic noise to transitions, because basically the way that these are done is I always assume it's in the steady state. Steady state is basically if I let my system run a long time, where does it eventually settle down to? Like if you sloshed a bucket of water, it would eventually, its steady state is just like flat and hanging out, no ripples, right? So QArray always assumed that everything was in the steady state, but it turns out that that's not true because there's actually a lot of fluctuations going on with things settling down. And so we get a higher quality approximation by adding in basically stochastic relaxation, which is where stochastic states will jump down at energy level. And this is more realistic. This is the exact picture. And you can see that it fits better. You see these rough edges. Well, these rough edges are realistic. Well, it turns out that there was also another drawback, in addition to not being as accurate by assuming the steady state approximation, because it's not true for the time scales once they're operating these systems. And that's that it's a lot more intensive to compute. So this gray line here is the steady state approximation. And because you assume everything's in the steady state, which is not true, you have to model each and every state. Because in the steady state, all states will be occupied a little because you've kind of sunk down into the ground state of the system. So it's no longer concentrated in some higher energy place. It turns out if you do this stochastic jump thing, you only have to model the states that are indeed occupied, that have been jumped into. Well, this scales polynomially. And so here's what it looks like you get on CPU, GPU, and multiple GPUs. You of course, as you go down the stack and get better hardware here, you have the speed up. But in both of these, you'll see a more polynomial scaling, and that's because you're doing less work because you're only modeling the states that matter. So here's an example of how you can not only model things better, but also much faster. And then similarly, if we talk about the quantum effects, so you'll see that this diagram differs because we get hybridization right here instead of these straight lines. If you add in the quantum effects, normally that grows exponentially because, as we know, 2 to the n, right? 2 to the n is how these quantum effects grow. But it turns out that we were able to capture this perfectly with way less compute, more of a polynomial scaling here. Here's the number of qubits, here's the compute time. We were able to capture this with way less compute by simply first modeling what states are relevant, what states are low enough energy that we actually care about them, getting rid of the rest. That number scale is like a high degree polynomial, and we were able to do the calculations for much cheaper. So this is just one more example of how human ingenuity you can really power ML by saying, no, let me take the time ahead of time, or in this case, we took the time afterwards, but oh well. And learn how to optimize the simulation so that I can get more data and better data for less. Okay, so those are the two projects I wanted to present to you where we're using kind of like human cleverness, human smartness to get more data and better data. For the rest of this talk, I'll be presenting you guys projects in which we use ML intelligence, or I guess artificial intelligence, right? In order to get more data quicker and better data, better quality data. And so the first project I want to show you that did this uses Fourier neural operators to do this. And it was done by Freya Shah, who is actually a Weiser alum. So Freya Shah herself, I was like, I don't know if I want to do this talk. And she's like, no, Weiser's excellent. You have to do it. So Freya Shah is a Weiser alum who did this. She is a student actually at Oxford also right now, but she did this work as part of her undergrad research at Caltech. But she actually went to undergrad in India, but she was a visiting research scholar who did this at Caltech. So she trained Fourier neural operators basically to be big, fast producers of quantum data that we could then use in downstream tasks to train AI models. So how did she do this, and why are these a good choice? There are these things called Fourier neural operators, which look a lot like other deep learning models, but they have a twist. So in every layer, and of course in all deep learning models, right, like there's many layers. In every layer, they have two paths that they follow. The first path is a traditional path where they take your data and they run it through a parameterized linear layer, which is just a fancy way of saying that there is a matrix that has some parameters in it, and those are what you update when you train the model. So you update so that the model works. So this is the first path, and they do follow that path. But they also split the data in two and send the other half of the data through what they call the Fourier pass. So the Fourier pass, they do a fast Fourier transform, They truncate the highest frequency mode so that they focus on the big picture. They now interact this with a parameterized linear layer, but this time it's Fourier space, right? So if it was, say, the Schrodinger's equation, if it was in time space, now it's in frequency space. And then they invert it back with an inverse Fourier transform so that it's in the same units that the original was. Now, these Fourier neural operators, or FNOs, I'm going to call them FNOs from now on, they're really good at learning differential equations because the Fourier transform is really good at breaking down the components of a differential equation. So Freya, knowing this, she said, I want to use this to basically to model the Schrodinger's equation. My dream is that I'm going to take these input states and I'm going to train the FNO to give me the output states, which would be what the Schrodinger equation, like, doing numerical integration on that, which is very expensive, what that would yield. And she indeed did that. And you can see at the top here, this is basically how her best training protocol. And she reached 100% fidelity after like really long time evolutions because she trained the FNO to actually learn how to integrate an input state so that she didn't have to do the numerical integration herself. So the reason why we want to do this is kind of twofold instead of just doing the traditional numerical integration. The first reason is because it's so much faster. It's about 1,000,000 times faster once you train one of these, literally 1,000,000 times faster to just get the output of your Schrodinger's equation from an FNO rather than do that numerical integration yourself. So this is, and you're going to see this reflected through several projects now going forward. This is like a big old data generator for quantum data that we can then use. This is like, if I want data to train my ML, a model to train my AI model, well, here's how we get it. That's first. The second one is really interesting and unique to the Fourier neural operator, or to neural operators in general, I should say, is that you can then reapply these. So you can train your FNO from time 0 to t, and then you can reapply it one more time to get to 2t. And you got inference on what's going on with your state at 2t, but you've never been to 2t before. You didn't train it on data from 2t. Go ahead then and reapply it 8 more times and get to 10t. You're now doing high quality inference on what's happening to states at 10t, but you've never even simulated states. You've never given any training data even past 1t. So you can do it way in the future, which can have, especially for quantum systems and tensor networks, really good speed up. Okay, so now this is what Freya did. A wiser alumni, Freya Shaw. That is what Freya did. And now we're going to see a lot of areas where people have gone on to use her work elsewhere in the quantum sciences. So the first person who took this and ran with it is Anastasia PP, and she is a PhD student at UCLA in the Neuron group. So Anastasia said, I like what you did, Freya, but I want to add one twist to it. I want to be able to vary the time dynamics of my system. I want to be able to put in any detuning vector. So she wanted to work with molecules, and if you control molecules in the lab, basically you shoot them with a laser, and you can change the energy of that laser, which is the same as changing the color of it just a tiny bit or changing the frequency. So we'll talk about frequency, but it's all the same, right? I want to be able to change basically this laser that's addressing how it's addressing my quantum system. And I want to be able to do that because I want to be able to control how molecules are prepared. I want to prepare molecules in a certain way. It is non-trivial to do so. It's counterintuitive to do so properly. So what I want to do is I want to train a forward model or a surrogate model for an FNO that I say, hey, for any input state and any detuning vector, you tell me what I get out, what that pulse sequence would have done to this molecule. If I can train that as an FNO, I now have this data generator that's 1,000,000 times faster. I call that my surrogate model or my forward model. It's 1,000,000 times faster. I can now train an inverse model and the inverse model works like this. I say, hey, inverse model, I want my final quantum state, my final molecular state to be prepared like this. Here's the distribution I want it to follow. Tell me what parameters, what input state, and what detuning vector do I need to choose? And the way that I actually can train this inverse model, the reason why this is not possible, whereas before it was impossible, is because I have this forward model, the surrogate model, that gives me data 1,000,000 times faster. Just with regular simulation, I can never do this, right? Because my inverse model is too data hungry. I need this forward model. I need this surrogate model. It makes data collection a breeze, and I can train this amazing inverse model that all I have to do is say, prepare me this state. And it's like, yes, ma'am. And that is something you could not do without these Fourier neural operators. So anyways, Anastasia did exactly this. She trained an FNO that she gave it any input state she liked. She gave it any detuning vector she liked, and it would tell her what the outcome would be. Then she tried various inverse models. They all worked, of course, because they were all rich with data. They had all the data they could eat. So, of course, they did a great job. And she was able to define pulse sequences for controlling states that no one folks had ever seen before. And again, all of this was possible because she had this big data machine that is the FNO. And I want to pivot for 1 second and talk about some work that Byung-Woo Kang did. He's also a PhD student at UCLA in the Neuron group. So he wanted to kind of take advantage of the other property of FNOs that I told you was super cool for quantum physics, and this is the time extrapolation. Because remember, with an FNO, I can train it from 0 to t, I can never have any training data that goes past t, but then I can reapply it again and get information, high quality inference, right, about what happened at time 2t. So Byung-Woo said, I think this is really interesting for tensor networks. Remember tensor networks, we talked about them before. We said they start off really easy, but the more gates you add, or the more time in your evolution, they grow exponentially complex. So he said, great, this is a perfect system for FNOs, because if I go from 0 to t, I could, there are many systems for which, for a tensor network, I can train that. But going to 2t, because this grows exponentially, would be so big and bad that I couldn't do it on even the biggest cluster in the world. So this is now helping me solve a problem I couldn't solve before, because it's very non-trivial for tensor networks going from t to 2t. It's exponentially harder instead of just linearly harder. So that's what he's doing. He's doing it for various different condensed matter problems, and he's getting quite far in it. And kind of the long and the short of this is it's going to take a while for this paper to come out, but when it does, you will see that using FNOs will help you do simulations with tensor networks that that to our knowledge, just no computer in the world can do, because they can take that, they can infer those time dynamics. And that's a really powerful thing in a modality like tensor network. And then I want to show you one more tensor network, one more FNO, not tensor network, but FNO derived inverse design problem. And this one is not for Schrodinger's time-dependent equation. It's for the basically spatially dependent equation. So this is to remind you guys that FNOs are really good at solving differential equations, right? Equations where we have the derivative and we say, hey, integrate it somehow, not just in the time domain, but also in the space domain. So this is Mark. He works, again, on quantum dots for at Oxford. He actually just graduated. I'm doing a postdoc now. And so Mark, he wants to, this is what he basically wants when he defines a quantum dot. He wants this whole density diagram. He knows what he wants it to look like. If you wake him up in the middle of the night, Mark can draw you exactly how he would like this to be to get good qubits. The issue is it's counterintuitive. The choices, the design choices to move between the design choices that Mark has, which are, again, these what we call gates, these are images that he's putting on a semiconductor material, and the voltages that he applies, it is counterintuitive to move from these design choices that he has control over to this whole density diagram, which describes how good his qubits are, that he knows what he wants. He can write down, again, without problem, exactly what he wants this to look like, but he cannot tell you what this needs to look like and what that needs to look like to get here. So this is another inverse design problem, right? He would like to have an inverse model where he says, hey, AI model, magic AI model, holy black box, tell me what to do here that I get some nice diagram like this. So he wants to train an inverse model like this, but we know what we've been learning throughout this talk, that to train an inverse model, you need a surrogate forward model. So he needs to train an FNO that can take this image and this image, these features that are carved in these gates and this voltage, and then tell him what this differential equation, what the output will be. So he trained an FNO to do this, that he used, and it was a million times faster, of course, because they're always like a million times faster. Just because the arithmetic is so much simpler than numerical integration once you have these models trained and optimized and frozen for inference time. And then he trained an inverse design model, and of course, it was rich with data. It had a million times more data than if he had done this the old-fashioned way, so it did a great job. And he came up with a great design, and the paper is pretty much done, but we're just waiting on someone to actually build it, because people were so excited, our collaborators were so excited about this design, they wanted to actually build it in the lab. And of course, that's a slow step. That's why we do these simulations, so we don't have to just build a million of them in a lab. We can just do a million of them in a couple seconds with an FNO. And so look out for this in the next couple of months. They're building it actively right now, and hopefully it's going to be the best quantum dot array of its class. It's going to be a small one, but it's going to be very high quality, and then we'll scale from there. And then I want to look at one more inverse design project with you guys. This one does not use FNOs. Okay, this one was done by Olivia Seidel and Faraz Abuzar, and they are PhD students. They both have like many affiliations, especially for PhD students. It's kind of crazy, but they both belong to Fermilab. So that's the affiliation I'm going to use. That's how I think of them as Fermilab students. So they work on superconducting qubits. So this is, again, a different modality. This is, probably the most well-solicited modality of qubit in at least back in the day in industry. Maybe that's changing with neutral atoms. But, Google works on these, and Rigetti works on these, and AWS works on these, and everybody uses these, right? So they work on superconducting qubits. So they had another inverse design problem. They said, okay, I want to know something called the qubit frequency and something else called the anharmonicity. These are things that if you study superconducting qubits, you'll learn all about, but we're just going to treat these as like engineering terms, right? The people who engineer these things, they know exactly what they want, and I just help them, right? There's a level of abstractions here. So for our purposes, just trust that the frequency of the qubit and the anharmonicity are important. Okay, they knew what they wanted, but they didn't know how to get there with the various design parameters that they had. Again, very technical engineering terms like claw length and ground spacing and other microelectronic stuff. Well, they not only had that, this pickle where they clearly need an inverse in it. They want to train an inverse model because they know what they want, but not how to get it. So they knew they needed a forward model, but they had a second kind of a cog, a second kind of stick in the wheel here that was complicating that a little bit. And that was that they only had very small data sets with which to train their forward model. So for certain problems they wanted to solve, they only had like 200 data points, which is tiny. And for other problems they wanted to solve, they only had like 1,000 data points, which is tiny. And that's because the simulation to get from what they wanted, from what they could control to what they wanted was so small, was so slow that they had these very small data sets, right? They're a national lab. They didn't have that much compute access or licensing for these sorts of proprietary simulations, and they were very slow simulations, so they had small data sets. So they got pretty clever, and they said, you know what, small data set, small model. I'm going to take a really small, simple model, a multi-level perceptron, which is like one of the like original kinds of like learning architectures, right? Only a few thousand parameters, and I'm going to train that. And they did, and it created this great, almost perfect forward model, which, shocked me. I was like, wow, I can't believe it worked so well. And then they used this teeny tiny little forward model to train a teeny tiny little inverse model that also did a great job, that produced on average only 0.5 percentage error and like 1 percentage error for these two metrics that are really useful. And depending on your application, this could be even a moderate amount of error, but actually for their application, the data sets are so noisy themselves that they say that this is probably the most accurate approach they've ever seen. And so again, this is just like a different model. In fact, a very simple model, not an FNO, but a simple multi-level perceptron, like one of the old grandparents of AI, of ML, right? And they were able to get incredible inference because they trained this surrogate model, this forward model. It was, in their case, it was 500,000 times faster. If the system was bigger, it'd be even bigger. And to be 500,000 times faster doing that simulation themselves, they get all the data they needed, and they could do a really nice inverse project. Okay, and now I'm going to get away for a couple minutes here from talking about inverse design, and I'm going to talk about diffusion models. And I'll stay on this point for a little bit, but this will be the last topic of this talk that I'll show you guys. So diffusion models, for folks who are not familiar, are really, really cool. That's what I want to start off by saying about them. They are generative models, which means that you basically want to train it on samples of something, and then it's going to produce new samples for you. So a lot of times these are used for image production, like DALL-E and stuff as a diffusion model. If you guys have been making figures and making pictures with DALL-E. So you basically, for instance, you would give it images of gentlemen, or you would give it images of cats. You'd train it with such images, and then it would produce brand new images of gentlemen and brand new images of cats that you've never seen before. So people like diffusion models technically because they have some really nice properties. They train really stably. They don't have mode collapse, meaning they give you really diverse images or whatever the different item that you're trying to get them to produce is. And they do this extremely like lifelike, okay? Like they don't just produce like a cartoon or a blurry image of a gentleman. They give you like a really lifelike image of a gentleman, which presumably you may need, right? So people really like these models for technical reasons, but I like these models because they're super freaking cool. They're really freaking cool, guys. So here's how they work. I think this is one of like conceptually, I think this is the very coolest AI model. I'm not saying like best overall. I'm saying conceptually the most cool. So the way these work is you take these images and you add noise to them, and the noise is lightly conditioned on what the image is like. And then you train an ML model to infer at every step of this adding noise. You might add noise to your gentleman, or you add noise to your cat, your pictures of your cats here. You train a model to inverse it at each time step by basically saying, what noise do I think was added? Okay, extract that noise. And then once it's trained, so you basically, you add noise to it, and then you train it to bring it back from the noise. And once it's trained, you can just give these models straight up random noise, and it will produce brand new pictures of gentlemen for you, brand new pictures of never before seen or conceived of cats for you from noise. And I just think that that's great. I think it's super cool idea, and it's amazing that it works. And it's also really nice because it has great kind of physics metaphors in it, right? All of physics, especially quantum physics, is like noisy diffusion. Right? That's what these noise channels look like. So one thing that I would like to do with this, but I haven't done yet, but I actually said this at a talk last week, and now 10 people want to do this with me, so I guess we'll be doing it soon, is I'd actually like to use diffusion models to design quantum computers. So like here's that quantum dot I showed you earlier. If it could build pictures of dudes from dudes and cats from cats, then why can't it build me pictures of quantum computers? Because many of these layouts are representative as an image. And also these don't have to be images. They could be layers of images, videos, whatever you like. They can generate molecules, all sorts of different data. So I think that we should do this. And I guess so many people are excited about doing this now that we will. But what I have already done, I haven't done this yet, we're just getting started, but what I have already done is the closer analogy, which is using diffusion models to denoise quantum systems. So now instead of taking a guy, having his picture get noisier and noisier, and training the model to bring it back to a guy, and then just correct all general noisy pictures of guys to solid pictures of non-grainy, non-noisy guys, we could do that with qubits. So I could take my noisy qubit, I could subject it to basically an error channel, right? We know that error is attacking our qubits all the time, and I could train my diffusion model to bring it back to a good qubit or register qubit, subset of qubits, what have you. So we have been doing this work, and it's about done now. I'm just harassing the poor grad student about making the figures look big and pretty and worthy of a high journal, right? So this work was done by Yuval Don. He's actually a PhD student at NVIDIA, not with me. In the United States, we don't really have PhD students, but they do in Israel, I guess. And so he's PhD student joined NVIDIA and Bar-Ilan University in Israel. So he has done exactly this. He took a noisy qubit register. He added noise to it. He allowed it to be basically acted upon by a noisy channel, which is very realistic, right? It happens all the time, whether we like it or not, to our qubits. And then he trained a model to bring it back from the noise to its original prediction. And he got really good results. So the median correction here was 99.8% fixed. So that's fantastic. But the only thing, this is a great work. I'm really proud of you, Bali. Did a great job, and I think this can be a great contribution to the field. However, we need to do further work on this because we broke a cardinal rule here. Remember I told you to be lazy? You have to be lazy in telling your model what to do. We were not lazy here. We told it to reconstruct the full density matrix. This scales exponentially. The amount of data you need to do that scales exponentially, which actually we should expect, right? Because the full density matrix scales not only like 2 to the n, but 2 to the 2 to the n. It's a terrible animal. So we should have expected this. We want it to scale polynomially, and so we'll have to do further iterations of this work where we give it a more kind of clever loss function. That's not the full freaking density matrix. That's too much freaking work, right? It's going to have to be some nice little compact expectation value or something like that. So anyways, diffusion models, their future in quantum is bright, and who knows, like maybe you guys will work on these as well. All right, and with that, I thank you guys for your attention, and if you folks have any questions or things like that.
Hi, Taylor. Thank you so much for the wonderful talk. We do have a bunch of questions on Discord, and I can read them out to you.
Sounds good. I'll just, I guess, keep the screen up in case the questions need the visuals.
Yeah, that sounds good. Okay. A question from Hiranmai. Could the same FNO framework be extended to optimize quantum gate control pulses in quantum computers, not just molecular systems?
Absolutely. Any pulse control sequence. The only thing I would say about it is what you're really learning with FNOs is, pardon me while I navigate here, what you're really learning about with FNOs is time dynamics. So for gates, it would be really good for optimizing how the gates are actually done with the pulses, which I believe is, kind of intimated in the question, right? What it would not be very good at doing is just a discrete gate, because that's not really, that's discrete and not really a time-dependent equation. But for optimizing the gates themselves, it's exactly what it should be done here. The fact that this is a molecule is kind of beside the point. This would work for any kind of modality of qubit. As long as you know the dynamics and can simulate them, it could tell you, it could fill in the nitty gritty of how that time integration is done.
Thank you. A question from Sunil Karki. Can I apply the ML to optimize the gate around the code during quantum error correction?
The gate around the code. I think the same, I guess it depends what you mean, but no matter what you mean, the answer is basically yes. Like if you mean, did they say FNO?
No.
They just said model code.
Just learning to optimize.
It's a little bit vague, but no matter what you mean, the answer is yes. So if you mean FNO, of course, if it's on this pulse sequence level of abstraction, then yes. If you're talking about these sampling things, then absolutely. If you adjust them to be more realistic, then you can simulate that. You could reapply this. It's a really flexible modality. So the exact answer of how will depend, on what exactly was meant by the question. But in general, the answer is yes.
Okay, thank you. Yeah, if there is a follow-up, I'll let you know. A question from Ajay Shankar from India. So with extension, can the FNO completely replace optimizers?
Yeah, as long as it's a good question. Probably there's some sort of hierarchical family of FNOs. You could use FNOs to train more complex FNOs and so on and so forth, but that I think would be an open research question. But in general, you can always train an FNO as long as you have a smooth enough differential equation that you're solving, and as long as you have some training data to train it. So you do have to pay the piper a little bit. You have to have that training data set to train it. But once trained, it's good to go on, from what I've seen of it, any kind of continuous smooth differential equation.
Mm-hmm. Thank you. Question from Dana Lakshmi. How accurate is the surrogate neural network compared to like a full ANSYS simulation?
That's exactly how they did this, right? So the surrogate neural network, the full ANSYS simulation, it's a, glad you're freaking out. The full ANSYS simulation is like ab initio, right? From first principles, it's like physics works like this, and I am simulating all the different individual parts of physics. They took this data set, and this is the beauty of ML. ML doesn't care about physics. It just knows patterns. So it didn't have to wipe so much faster. It's because it learned to extrapolate from this data. It didn't model the physics at all. It actually has no idea that physics exists. It has no concept of existence or anything like that, right? It just knew how to match the pattern. So we needed that ANSYS data to teach it the pattern. But once it had the pattern, it was taking a huge shortcut and just beelining right to the answer.
Thank you. That's great. Question from Yagna. Could diffusion models be combined with reinforcement learning to jointly optimize quantum gate operations and noise mitigation?
Absolutely. Yeah, you can take this diffusion model, what it's going to give you, I don't know, whichever picture of this you like. I actually prefer the gentleman and the cats. You could take this and get it to give you whatever quantum data that you like. It could be a data generator, and then you can then use that, plug that into an RL model to further optimize. Because in this case, this would be basically your surrogate data, right? This is going to be faster than doing the simulation yourself. It's not quite as fast as an FNO though, huh? That's the major drawback of diffusion models, is that their inference is a little slower, but certainly it's faster than most simulations, like actual first principle simulations. And then you could use that to plug into just about any model, be that an inverse model or just a model that's a decision-making model like RL. Absolutely, you can combine models in this way. And people do.
Thank you.
And they do. Not for quantum yet. We'll get there, but they do for other things.
Got it. Thank you. Question from Megan from University of Michigan. What is the decision framework for selecting an AI architecture? And there's a follow-up question from her. Where do FNOs begin to fail? And how do you detect when an FNO is extrapolating beyond its reliable regime?
Good questions. Okay, so I guess I'll do in order because they're all a little different. Yep. So the first one's, how do you pick an architecture? It really depends. It's a vibe, you know what I mean? It comes with experience. That's actually a lot of the work I do. Like if you see on these slides, you see that repeatedly there's a lot of other people on them. What do? Is I help them pick an architecture for the most part. It's dark magic. But usually it's like, well, it can be very well motivated from your understanding of the physics and of the AI model. So like with the physics here, say in this project and all the projects that came from it, we know that the physics is that Schrodinger's equation is at its heart a differential equation. That's what it is. And then understanding the AI architecture part of it, it's like, okay, FNOs are good at learning differential equations because the Fourier transform basically picks out the essence of differential equations. So those two things together, you can say, okay, put this together, and that you kind of do it like that, and then it doesn't always work, and then you try something else. I think her next question, could you tell me her other two questions?
Yeah. Where do FNOs begin to fail, and how do you detect when FNO is extrapolating beyond its reliable regime?
So an FNO begins to fail. First of all, it could fail right off the bat if you're giving it something that's it's not well suited for. So FNOs themselves are not great at, say, noisy data. So it'll fail pretty quickly with that. For that, you need a Markov neural operator, which also works great, but it'd be the wrong model if you have like noisy data. They can also fail if you have like discrete pulses, like discrete gates, instead of integrating an actual differential equation. That's not the right model for this. And then they can also fail, which I think her question is kind of alluding to, if they're extrapolated for too much time. So they begin to fail when they don't have enough information, basically. So when they haven't learned, let's say when they haven't learned the differential operator, that's basically the stand-in for doing the old-fashioned numerical integration well enough. So actually you can see this really good in this plot. So this pink line was the proper way Freya found out that this was the proper way to train the FNO. And this is actually extrapolating 11 times later than she initially trained it. Okay, and you can see it's hanging out, it's chilling at 100% fidelity, it's happy. These other ways, let's take the green one. The green one does a pretty good job at first, but then it begins to fail. And why? Because this particular instantiation of the FNO, Freya learned, was like not good enough at learning the time dynamics. It actually only learned like a local region of time dynamics, such that when the state started to kind of evolve out of that, it started to fail. So that's how Freya knew that this wasn't the way to train the model. So here you can see, yeah, some of them start to do really poor after a period of time, and that's because they haven't learned the time dynamics well enough. So if you learn the time dynamics perfectly, you can apply this infinity times, it's going to work, up to your numerical precision. But if you only learn the time dynamics so, it's going to start to fail a lot earlier.
Yeah, got it. Thank you. How does a diffusion model compare with like reinforcement learning or Bayesian optimization for the inverse quantum device design?
Yeah, it's just really so different, right? So, okay, gosh, it's so different. Like diffusion models are inherently generative. RL doesn't have to be, right? It's more of like a decision-making process. So I'd say that you could use them sometimes for the same things, but oftentimes one of them is much more natural. For image generation, like you could do RL, but that's real hard, right? Like you're like, RL, build me a picture of a man, pixel by pixel, make decisions. That's less natural. Same thing with diffusion models. You could be like, diffusion model, produce me a control sequence, and it could do it, but that's not as, it's not really in the spirit of generative diffusion. But they also have other pros and cons globally, even though you'd very rarely use them or try to use them for the same sort of application. Like, for instance, RL in theory can be faster, but oftentimes is not, because it's not very stable at training time. Like you might all of a sudden have catastrophic forgetting, they call it, where I was doing good, I was making progress, and then bam, like, oops, I made a bad decision. And now I'm totally in an area of parameter space that's not good, and I'm trapped here again. Whereas the fusion models train really, really stably, and they don't suffer from that. So it just depends on what you're trying to do.
Thank you. A question from Rushi Raj. How do you decide the compatibility with respect to the usage of gates and algorithms to gain a quantum advantage with respect to like some of the application areas you discussed?
Yeah, so in my own research, there's all sorts of people doing all sorts of things. Some people do algorithms, they try to find quantum advantage. I used to do that a little bit in grad school. I personally kind of moved away from that because my research interests are no longer necessarily on the finding of an algorithm that does quantum advantage, right? Presumably that's what we do all this for. But what I'm really interested in is big compute and AI to help make that possible. So if you look at these sorts of projects that I've shown you, our loss function is never quantum advantage, right? Like, inherit super polynomial speedhook over a classical algorithm. It's never that. It's whatever component that my elders and betters, my much smarter collaborators know that they need to get their device, their control sequence or whatever to a point where it's more suitable, like a better candidate for actually doing quantum advantage. So I think it's important to separate the algorithms and what algorithms could lead to quantum advantage from here's what I know I need to do about building my device, controlling my device, characterizing my device, understanding my device, to even have it where it could do these operations that are required by these algorithms that might have quantum advantage.
Thank you. A question from Reza. Can this method be applied to defect detection on a chip?
So again, can Reza clarify maybe if they're in the chat, which method?
All right. Okay, I'm going to ask that, and maybe we can skip to another question while they reply.
Yeah, maybe come back to that one when they clarify which method.
Okay, sounds good. Question from Pranita. If you had to build an AI plus quantum project in just 1 week that would impress recruiters, what problem would you choose and why?
What was the last part? That would what?
That would impress recruiters.
Okay, good question. I'm going to answer that question in two ways. So first, I'll address maybe the impressing recruiters way. I wouldn't focus on impressing recruiters, honestly. Like, I think that just because not that I'm not like I sit on a holy high horse and I'm like, don't worry about impressing recruiters. But I really think that so much of this quantum research stuff, it's more academic in nature, even when it's industrial, right? So I would not focus on the 1 week time scale for job opportunities. I'd focus on going to grad school and doing good work in grad school. A lot of this research really requires a PhD, so I would take that route to it. I'm not saying like, well, this is the only way to do it. I did it that way, and that's how one should do it. I'm just saying that is the well-formed path in which these things are done. And I think oftentimes it's the best way, right? It has a lot of oversight, a lot of opportunities for learning. So I wouldn't focus on impressing recruiters. But if I wanted to put together, so maybe I'll tweak the question then. If I wanted to, spend 1 week to impress my advisor or my advisor's, friends, the advisors have other old people, professor, or like myself, old lady, industry friends, right? What model would I do there? I would do this. I would go talk to their grad students, to them, or if I couldn't get a hold of them, I talk to their grad students, their postdocs, whatever. I would say, what's a problem in your lab? And then that you're dealing with as you try to build these things or optimize these things. And then probably I'm not an expert in that, right? And so I would say, no, help me understand. What does that really look like? Is this a matrix? Is this a vector? Is there an area of learning space we can focus on? Because if I focus on the whole thing, I'll never learn it. I need a specific application. And I would have them help me put together something that's of use to them. Because that's really what everybody needs is people don't care what other people could do or what they can know. They care about what you can do for them. So I would go right to the problems that they're having, and I would start working with the people who do know about those problems to find a solution for them.
Yeah, thank you. That's a great answer. A question from Vishal from India. Could this batching strategy be combined with classical optimization algorithms to automatically focus computations on the most probable error trajectories instead of uniformly sampling all the time?
Absolutely. And that is something that actually was, I try to keep it a little brief here, but that's actually one of the things that we did. If you read the full paper, you could choose. This is a design that you could focus on any part of error space, and we wrote several algorithms for that. But other algorithms could plug right in. So you could say, tell me about the most common errors. You could say, tell me about the less common errors. Rare event sampling really kind of took off after this paper came out. Sometimes, like people have a ton of data on the most common errors because regular simulators get you that data really quickly, but not the rare errors. You could say focus on certain errors that involve these qubits or that involve these combinations of different errors occurring or that cause this type of error that I'm having a hard time correcting my actual device. You could choose anything you want, and that's the beauty of this factorization technique is it gives you fine-grained control, not only of how many shots you take and win, but measurements you take and win, but also the errors that you study.
Thank you. I think Reza clarified. So I think it means more broadly, can any of the methods you discussed be applied to chip defect detection instead of using conventional models like UNet or CNNs?
Of course, yeah. And so, okay. Well, so a lot of things, here's the deal. Yes, for sure. But you're probably going to have an easier, it depends how you conceptualize your chip, right? But if you conceptualize it in a pictorial way, you're probably going to use CNN at some point. So this transformer thing, we focus a lot on the transformer, but look at this sneaky CNN. I mean, CNNs are really good at getting them features from your images at different levels of abstraction, which is so much of what you need to do when you need to make decisions on visual type output. So, we almost never in like modern AI use just a CNN. At least we church it up and make it like a UNet, which is mini CNNs and stuff like that. And usually a transformer model or something like that stuck in there as well. But yeah, a lot of times there'll be a CNN involved. I mean, certainly maybe with something like different things, right? So okay, maybe something like these MLPs, these multi-level perceptrons. Perhaps you could, not, if you're looking at a chip defect and you're saying, well, I actually suspect the chip defect, or I think an ML model could correctly identify one by patterns in the frequency and the anharmonicity, where they are and how they correspond to each other, that would correspond to a defect. Then you could detect it maybe somehow this way with the readout, which might not be like a picture at all. It might be just a few discrete or a few continuous values. With the fusion models, I mean, certainly this is a totally different way of manipulating images that doesn't need a CNN. Like you could definitely, the fusion models are really good at things like in painting. So maybe like once you could, you could do conditional the fusion models where you tell it to look for certain things or do certain things. And that's called in painting. When you say, hey, look at that area, change it. So you might tell the CNN, or part of CNN, you might tell the diffusion model, hey, when you see an area that looks like this, and this corresponding to a defect, change it. So yeah, there's a lot of different things that you can do, but a lot of times, CNNs are somehow part of your equation. Not necessarily like in these last two cases, but a lot of times CNNs are just like a great little workhorse component for visual type data.
Thank you. We're almost out of time. Maybe one last question. Something that I was curious about when I was how fast like these large language models are advancing, and I've seen Google's recent work on like Alpha Evolve and kind of discovering new algorithms. And do you kind of see some of them being useful in your own work in either like discovering like new algorithms for doing some of the work that you illustrated here, or how it can be integrated more with this pipeline?
Yeah, no, I think so for sure. We do have a project I didn't talk about because it's still very much underway and involves many folks, and so I don't want to scoop them. I don't want to give it away, and then maybe one of you
Yeah.
smart young people who's much faster than us old people will just go do it. It uses this idea, right? Yeah, it uses these alpha evolve type ideas to kind of morph the way that we control molecular systems, which is generic enough that it's not going to scoop anything. But yeah, like I definitely do think so. But you're right though that if you look at the research projects that I've shown you, mostly I'm not worried about, and most of them not using large language models. And I think that's not because they're not powerful. They're extremely, extremely powerful. I think the reason I tend to shy away from them a little bit is just because there's already so many people out there doing great work in them that one of the I'll stop sharing here. One of the criteria that my boss's boss has for the research that we do is that it shouldn't be Me Too research. It should be research that no one else is going to do. If you didn't exist, no one else would do it. And so I guess that's what I'm trying to do. I'm trying to explore the areas that other folks don't happen to be looking at the moment.
Awesome. Thank you so much. And yeah, thank you so much for taking the time to come talk to us today, and also thanks to Freya for like encouraging you to give this talk. We really appreciate it. And thanks for sharing her journey with us. It's like nice to see the WISER community kind of go out and do all this like amazing stuff in the world. Yeah, thank you once again for taking the time to come talk to us today. This is all like such excellent work, and you gave such a broad overview of all the different projects. And I'm sure it's going to inspire many of our participants to like really get deep into it.
Thank you so much, and so wonderful to meet you all, and thank you guys for doing this. It seems like such a great project. I do wish we had something like this when I was back in the Stone Ages, when I was these kids' age. So thank you guys for what you do, and I look forward to seeing you guys around.
Thank you.
See you guys.